Okay, well, I'd like to save a little time, but I'll very quickly, you don't have to reproduce this sketch. I just want you to, I remember very well from Friday to Monday, but I can't expect you do for a variety of reasons. Mainly, I have to think about this stuff all weekend, and God forbid. So here's the picture, and I won't anymore explain what's in it, but except there's the mass, here is the spring constant, the spring with its constant here, here is the dashpot with its constant. The equation is, from Newton's law, mx double, so this will be x, and here's, let's say, his equilibrium point is over here. It looks like mx double prime, we derived this last time, plus cx prime plus kx equals 0. And now if I put that in standard form, it's going to look like x double prime plus c over m x prime plus k over m times x equals 0. And finally, the standard form in which your book writes it, which is good, it's a standard form in general that is used in the science and engineering courses. One writes... One writes this as, just to be perverse, I'm going to change x back to y, okay? Mostly just to be eclectic, to get you used to every conceivable notation. So I'm going to write this as change x to y, so that's going to be on y double prime. And now this is given a new name, p, except to get rid of lots of 2's, which would really screw up the formulas. Make it 2p. You'll see why in a minute. So there's 2p times y prime, and this thing we're going to call omega naught squared. Now that's okay. It's a positive number. Any positive number is the square of some other positive number. Take its square root. You'll see why. It just makes the formulas much pretty to call it that. And it makes it also a lot of things much easier to remember. So all I'm doing is changing the names of the constants in that way in order to get better formulas. Easier to remember formulas at the end. Okay, now we're interested in the case where there's oscillations. In other words, I only care about the case in which this has complex roots. Because if it has just real roots, that's the over-damped case. I don't get any oscillations. Oscillations is by far the more important of the cases, two cases. I mean, just because, I don't know, I could go on for 5 minutes listing things that oscillate. Oscillations, like this, or they could oscillate by going to sleep and waking up and going to sleep and waking up. They could oscillate, Okay, so that means we're going to get complex roots. The characteristic equation is going to be r squared plus 2p. So p is a constant now, right? Often p I use in this position to indicate a function of t, but here p is a constant. So r squared plus 2p times r plus omega naught squared is equal to 0. Now, what are its roots? Well, you see right away the first advantage in putting in the 2 there. When I use the quadratic formula, it's negative 2p over 2. Remember that 2 in the denominator. So that's simply negative p. And how about the rest? Plus or minus the square root of, now do it in your head, b squared, 4p squared minus 4 omega naught squared. So there's a 4 in both of those terms. When I pull it outside, it becomes a 2. And then the 2 in the denominator is lurking, waiting to annihilate it. So that 2 disappears entirely, and what we're left with is simply p squared minus omega naught squared. Now, whenever people write quadratic equations and arbitrarily put a 2 in there, it's because they're going to want to solve the quadratic equation using the quadratic formula, and they don't want all those 2's and 4's to be cluttering up the formula. That's what we're doing here. Okay, now, the first case is where p is equal to 0. This is going to explain immediately why I wrote that omega naught squared. As you probably already know from physics. If p is equal to 0, the mass isn't 0, otherwise nothing good would be happening here. It must be that the damping is 0. So p is equal to 0 corresponds to undamped. There is no dash pot. The oscillations are undamped, and the equation then becomes, the solutions then are, well, the equation becomes the equation of simple harmonic motion, which I think you already are used to writing in this form. And the reason you're writing in this form, because you know when you do that, this becomes the circular frequency of the oscillations. The solutions are pure oscillations, and omega naught is their circular frequency. So right away from the equation itself, if you write it in this form, you can read off what the frequency of the solutions is going to be, the circular frequency of the solutions. Now, the solutions themselves, of course, look like, the general solutions look like y equal, in this particular case, there is no, the p part is 0, this is 0, it's simply, so in this case, r is equal to omega naught I times omega naught, plus or minus, but as before, we don't bother with the minus sign since one of those roots is good enough. And then the solutions are simply C1 cosine omega naught t plus C2 sine omega naught t. That's if you write it out in the sign, and if you write it using the trigonometric identity, then the other way of writing it is that A times the cosine of omega naught t, but now you'll have to put in a phase lag. So you have those two forms of writing it, and I assume you remember the little triangle which converts one into the other. Okay, so this justifies calling this omega naught squared rather than k over m. And now the question is, what does the damped case look like? That's more, requires a somewhat closer analysis, and it requires a certain amount of thinking. So let's begin with an epsilon bit of thinking. So here is my question. So in the undamped case, how do I get, I want to be sure that I'm getting oscillations. When do I get oscillations if, well, we get oscillations if those roots are really complex and not masquerading. Now, when are the roots going to be really complex? This has to be, the inside has to be negative. P squared minus omega squared must be negative. P squared minus omega naught squared must be less than 0, so that we're taking the square root of a negative number and we're getting real complex roots. Really complex roots. In other words, now this says, remember these numbers are all positive, P and omega naught are positive, so the condition is that P should be less than omega naught. In other words, the damping should be less than the frequency, the circular frequency. Except P is not the damping, it's half the damping or twice, it's half the damping, and it's not really the damping either because it involved the M2. You better just call it P. Naturally, I could write the condition out in terms of C, M, and K, so your book does that, but I'm not going to. Gives it in terms, gives it in terms of C, M, and K, which somebody might want to know, but, you know, we don't have to do everything here. Okay, so let's assume that this is true. then what does the solution look like? Well, we already experimented with that last time. I'm going to first draw it. Remember, there was some guiding thing which was an exponential, and then down here we wrote the negative. So this was an exponential. In fact, it was the exponential e to the negative p t. And in between that, the curve tried to do its thing. So the solution then looks sort of like this. It oscillated, but it had to use that exponential function as its guidelines, as its amplitude, in other words. Now, this is a really, truly terrible picture. It's so terrible it's unusable. Okay, this picture never happened. Unfortunately, this is not my forte, along with a lot of other things. All right, let's try better. Here's our better picture. Okay, there's the exponential. At this point, I'm supposed to have a lecture demonstration. You know, it's supposed to go up on the thing so you can all see it, but then you wouldn't be able to copy it, so at least we're on even terms now. Okay, how does the actual curve look? Well, I'm just trying to be fair, that's all. Okay, after a while, the point is, let's try to... So just so we have something to aim at, let's say. Okay, here we're going to go. We're going to get down through there, and then this is good. This is our better curve. Okay. So I am a solution. A particular solution satisfying this initial condition. I started here, and that was my initial velocity. The slope of that thing gave me the initial velocity. Now, the interesting question is, the first, in some ways, the most interesting question, though there'll be others too, is, what is this spacing? Well, that's a period. And now, the period would be, it's half a period. I clearly ought to think of this as the whole period. So let's call that, I'm going to call this pi over, so this spacing here, from there to there, I'll call that pi divided by omega 1, because this, from here to here, should be, I hope, twice that, 2 pi over omega 1. Now, my question is, so this, for a solution, it's, in fact, is going to cross the axis regularly in that way. My question is, how does this period, so this is going to be its half period. I'll put period in quotation marks because this isn't really a periodic function because it's decreasing all the time in amplitude, but it's trying to be periodic. At least it's doing something periodically. It's crossing the axis periodically. So this is the half period. 2 pi over omega 1 would be its full period. What I want to know is, how does that half period, or how does omega 1 is called its pseudo-frequency. This should really be called its pseudo-period. Everything's pseudo, everything's fake here. You know, like the amoeba has its fake foot and stuff like that. Okay. So this is its pseudo-period, pseudo-frequency, pseudo-circular frequency, but that's hopeless. I guess it should be circular pseudo-frequency or pseudo, I don't know how you say that. I don't think pseudo is a word all by itself, not even in 1803. Circular. Okay, here's my question. If the damping goes up, this is the damping term. If the damping goes up, what happens to the pseudo-frequency? frequency is how often the curve how this is high frequency and this is low frequency. Okay? So my question is, which way does the frequency go? If the damping goes up, does the frequency go up or down? Down. I mean, I'm just asking you to answer intuitively on the basis of your intuition about how this thing explains, how this thing goes. And now let's get the formula. What, in fact, is omega 1? What is omega 1? The answer is, when I solve the equation, so R is now, so in other words, if omega 1 is, if I have P, if P is no longer 0, as it was in the undamped case, what is the root now? Okay, well, the root is minus P plus or minus the square root of P squared. Now I'm going to write it this way, minus, to indicate that it's really a negative number, omega squared minus P squared. Now, I'm going to call this, because you see when I change this to sines and cosines, the square root of this number is what's going to become that new frequency. I'm going to call that minus P plus or minus the square root of minus omega 1 squared. That's going to be the new frequency. And therefore, the root is going to change so that it's the corresponding solution then is going to look how? Well, it's going to be e to the negative pt times, let's write it out first in terms of sines and cosines, times the cosine of, well, the square root of omega 1 squared is omega 1, but there's an I out front because of the negative sign in front of that. So it's going to be the cosine of omega 1t plus c2 times the sine of omega 1t. Or if you prefer to write it out in the other form, it's e to the minus pt times some amplitude, which depends on c1 and c2, times the cosine of omega 1t minus the phase lag. Now when I do that, you see omega 1 is this pseudo-frequency. In other words, this number omega 1 is the same one as I've identified here. And why is that? Well, because what are two successive times? Suppose the solution crosses the x-axis for the first, the t-axis. For the first time at the point t1, what's the next time it crosses at t2? Let's jump to the 2 times it crosses. So this is I want this to be a whole period, not a half period. What's t2? Well, I say that t2 is nothing but 2 pi divided by omega 1, and you can see that because when I plug in, if it's 0, if I have a point where it's 0, so omega 1t minus phi, when will it be 0 for the first time? Well, that will be when the cosine has to be 0, so it'll be some multiple of, it'll be, say, pi over 2. Then the next time this happens will be, if that happens at t1, then the next time it happens will be at t1 plus 2 pi divided by omega 1. That will also be pi over, that will be pi over 2 plus, how much? Plus 2 pi, which is the next time the cosine gets around and is doing its thing, becoming 0 as it goes down, not as it's coming up again. In other words, this is what you should add to the first time to get this second time that the cosine becomes 0 coming in the direction from top to the bottom. So this is in fact the frequency with which it's crossing the axis. Now, notice, gee, I'm running out of boards. What a disaster. In that expression, take a look at it. I want to know what depends on what. So, P. In that, we got constants. We got P, we got phi, we got A. What else we got? Omega 1. What do these things depend upon? You got to keep it firmly in mind. This depends only on the ODE. It's basically the damping. It depends on C and M. It's essentially, it's C over 2M actually. How about phi? Well, phi, what else depends only on the ODE? Omega 1 depends only on the ODE. What's the formula for omega 1? Omega 1 squared. Where do we have it? Omega 1 squared, I never wrote the formula for you. So we have omega naught squared minus p squared equals omega 1 squared. What's the relation between them? That's the Pythagorean theorem. If this is omega naught, then this omega 1, this is p. They make a little right triangle, in other words. The omega 1 depends on the spring. So it's equal to, well, it's equal to that thing. So it depends on the damping, and it depends upon the damping, and it depends on the spring constant. How about the phi and the A? What do they depend on? They depend upon the initial conditions. So this mess of constants, they have different functions. What's making this complicated is that there are 4 parameters. Our answer has 4 parameters, needs 4 parameters to describe it. This tells you how fast it's coming down. This tells you the phase lag. This tells you this amplitude modifies the e to the minus. It tells you whether the exponential curve starts going like that or goes like this. And finally, the omega 1 is this pseudo frequency, which tells you how it's bobbing up and down.